Welcome back to the .NET Way. You're watching episode 19 of our .NET Core interview series. Today, we're diving into one of the most important software architecture concepts in modern backend engineering, microservices. Let's ask Aarohi what microservices really are, why companies adopt them, and how developers convert large monolithic .NET applications into scalable distributed systems.
Thanks. Microservices can dramatically improve scalability, deployment speed, and team independence. But they also introduce entirely new challenges around distributed systems, communication, monitoring, consistency, debugging, and infrastructure complexity. Many developers think microservices are just smaller APIs, but in reality, they completely change how software systems are designed and operated.
Aarohi, let's begin with the basics. What exactly is a microservice?
A microservice is a small, independently deployable service responsible for a specific business capability. Each service owns its own business logic, its own database, its own deployment pipeline, and often its own development lifecycle. Instead of building one massive application containing everything, we split the system into smaller services focused on individual domains like orders, payments, inventory, or notifications.
Can you compare microservices with monolithic architecture?
In a monolith, everything usually runs inside one application and often shares the same database. That makes development easier initially, but as the application grows, deployments become risky, scaling becomes difficult, and teams start stepping on each other's code. Microservices split the system into independently deployable services, allowing teams to scale, deploy, and evolve different domains separately.
Why do companies invest so heavily in microservices?
The biggest advantage is independent scalability. For example, an e-commerce company may need to scale only the order service during sales events instead of scaling the entire application. Microservices also improve deployment speed, team ownership, and fault isolation. A failure in one service is less likely to crash the entire system.
Are there situations where microservices are the wrong choice?
Absolutely. Microservices introduce network communication, distributed failures, monitoring challenges, deployment complexity, and infrastructure overhead. For small applications or early stage startups, a modular monolith is often a much better choice. Many teams adopt microservices too early and accidentally make development slower instead of faster.
How do you begin converting a monolith?
The first step is identifying bounded contexts using domain-driven design principles. We look for business domains that can operate relatively independently. For example, order management, payments, inventory, shipping. Each domain gradually becomes its own service with independent ownership and deployment.
What's the safest migration strategy?
The safest strategy is incremental extraction. Instead of rewriting everything at once, we slowly move one domain at a time into separate services while the monolith continues running. This approach is often called the Strangler Fig Pattern. It reduces migration risk and allows teams to modernize systems gradually.
Do services always communicate through HTTP APIs?
Not always. Microservices commonly use REST APIs for synchronous communication, gRPC for high-performance internal communication, message brokers like RabbitMQ or Kafka for asynchronous communication. Modern scalable systems heavily prefer event-driven communication because it reduces tight coupling between services.
Why do large systems prefer messaging so much?
Because distributed systems fail constantly. If service A directly calls service B synchronously, a temporary outage in service B can break the entire workflow. With asynchronous messaging, services become more resilient because they communicate through events instead of immediate blocking requests. This dramatically improves scalability and fault tolerance.
Why not let clients call services directly?
An API gateway acts as a centralized entry point for all client requests. It handles routing, authentication, rate limiting, monitoring, caching, and security policies. API gateway, front-end applications would need to manage dozens of individual service endpoints directly.
What gateway technologies do .NET teams commonly use?
In .NET ecosystems, YARP and Ocelot are very popular. YARP is developed by Microsoft and is becoming increasingly common because of its performance and flexibility. Large enterprise environments may also use Kong, Nginx, or cloud-native API management platforms.
Can multiple services use one shared database?
That's usually considered a major anti-pattern. Each microservice should own its own database. If multiple services directly share the same database tables, they become tightly coupled again, which defeats one of the main goals of microservices. Instead, services communicate through APIs or events.
If databases are separate, how is consistency maintained?
In distributed systems, consistency becomes much harder. Microservices usually rely on eventual consistency rather than immediate consistency. Patterns like Saga Pattern, Outbox Pattern, event-driven synchronization help coordinate workflows safely across multiple services.
We hear this term a lot in distributed systems.
The Saga Pattern manages workflows spanning multiple services. Instead of using one giant database transaction, each service performs its own local transaction and publishes events for the next step. If something fails midway, compensating actions are triggered to undo previous operations safely. This is critical in distributed systems where traditional ACID transactions don't work across services.
Does every service manage authentication separately?
Usually, no. Authentication is typically centralized, using OAuth 2, JWT tokens, OpenID Connect, or Identity Server. Services trust a centralized identity provider and validate incoming tokens. For internal service-to-service communication, companies may also use mutual TLS or API tokens.
What infrastructure is commonly used?
Most modern microservices are containerized using Docker. For orchestration and scaling, companies commonly use Kubernetes. CI/CD pipelines automatically build, test, deploy, and monitor services independently. This infrastructure automation becomes extremely important as the number of services grows.
What challenges surprise developers the most?
The biggest shock is realizing distributed systems are fundamentally harder than monoliths. Now developers must handle partial failures, network latency, retries, distributed tracing, message duplication, timeout handling, observability. Debugging distributed systems is significantly more difficult than debugging a single application.
How do companies monitor dozens of services?
Monitoring becomes absolutely critical. Without centralized observability, developers cannot understand what's happening across distributed services. Modern systems use distributed tracing, centralized logging, metrics dashboards, correlation IDs, health checks to track requests across multiple services.
How do services find each other dynamically?
In cloud-native systems, services constantly scale up and down. Hard-coding IP addresses becomes impossible. Service discovery systems automatically track available service instances and route traffic dynamically. Kubernetes handles much of this internally using DNS and internal networking.
Some developers think microservices automatically improve performance. Is that true?
Not necessarily. Microservices improve scalability and team independence, but network communication introduces latency. A badly designed microservices architecture can actually perform worse than a well-designed monolith. That's why architecture decisions should always be driven by business and scaling requirements, not trends.
Let's finish with your best practices checklist.
The biggest rule is this: microservices are not just a coding style, they are a distributed systems architecture. Once applications become distributed, complexity increases dramatically around networking, consistency, monitoring, deployment, and operations. Teams should adopt microservices only when the business genuinely needs independent scalability and service ownership. If designed properly, microservices can power extremely scalable enterprise platforms used by millions of users worldwide.
Excellent explanation, Aarohi. Microservices can completely transform how large systems scale and evolve, but they require strong architectural discipline and operational maturity. If this episode helped you understand the reality of microservices, don't forget to smash the like button, drop your questions in the comments, and subscribe to the .NET Way. Now, a quick update for our viewers. In episode 20, we'll be discussing design patterns in .NET Core, exploring which patterns Aarohi actually uses in real enterprise projects. But you don't have to wait until then. We have already created an entire dedicated deep dive series on design patterns. I highly recommend checking out that playlist right now for detailed interview-ready knowledge. The link is in the description. Thanks for watching. See you in the next one.